You flip a light switch. The light turns on. Simple, right? Electricity flows through the wires from the power plant to your house. Through the copper, down the cable, into the bulb. Except that's not what happens. That's not even close to what happens. The electricity, the energy that makes your light bulb glow, never travels through the copper wire at all. It travels through the space around it. Through the air. Through the insulation. Through what you thought was empty, nothing. And I'm going to show you that everything you thought you knew about electricity is wrong. When people think about electricity, they imagine it like water in a pipe. Electrons flowing through copper like water through a hose. The power company pushes electrons through the wire. They arrive at your house. They light your bulb. Clean, simple, intuitive, and completely wrong. Let's start with a basic fact that should make you suspicious. You have a wire, copper, good conductor. Inside that wire are electrons, trillions and trillions of them. They're already there, sitting in the copper, even when nothing's plugged in. When you connect a battery or flip a switch connected to a power plant, you create an electric field. That field pushes on those electrons. They start drifting through the copper. Now here's the question. How fast do those electrons actually move? Take a guess. Seriously, how fast? The speed of light? No. 1,000 miles per hour? No. 100 miles per hour? Not even close. Electrons in a typical wire drift at about 1 millimeter per second. 1 millimeter per second. That's slower than a snail. A literal garden snail moves about 10 millimeters per second. Electrons in your house wiring move 10 times slower than a snail. Now think about that. Your light switch is 10 meters away from the bulb. If electrons had to physically travel that distance at 1 millimeter per second, it would take them 10,000 seconds. That's almost 3 hours. But when you flip the switch, the light comes on instantly. Not in 3 hours. Not in 3 seconds. Instantly. If your mind is already spinning, drop a comment right now, because this is just the beginning. So, if the electrons aren't carrying the energy, what is? If the energy isn't traveling through the copper, where is it traveling? The answer is going to sound crazy. The energy flows through the space around the wire. Not the copper, the space. And the reason this happens involves something invisible. Something that fills all of space. The electromagnetic field. Let me show you what's really going on. When I tell people that energy flows through space, not copper, they look at me like I'm insane. But electrons are moving, they say. Current is flowing. What are you talking about? They're right. Electrons do move. Current does flow. But those electrons aren't carrying energy the way you think. Think of it like this. You have a pipe. A long pipe. Completely full of marbles. Packed edge to edge. You push one marble in at one end. What happens? Instantly, a marble pops out the other end. Did the marble you pushed travel the entire length of the pipe? No. That marble barely moved at all. It pushed the marble next to it, which pushed the next one, which pushed the next one. The push traveled, the wave of force, the disturbance, but no individual marble traveled the whole distance. Electricity works the same way. When you flip a switch, you don't send electrons down the wire from the power plant. You send a signal, an electromagnetic wave. That wave travels at nearly the speed of light, about 200,000 kilometers per second through copper. That's why your light turns on instantly. Not because electrons race down the wire, because a signal, an electromagnetic disturbance, propagated through the wire at nearly light speed. The electrons themselves, they're barely crawling. They're just responding to the field. Now here's where it gets interesting. That electromagnetic wave, that signal that tells the electrons to start moving, doesn't actually travel inside the copper. It travels in the space around the copper. Let me say that again, because it's important. The electromagnetic signal that makes your lights work travels through the space surrounding the wire, not through the metal itself. The wire just guides the wave, like a rail guides a train. But the energy? The actual energy? That flows through space. How do we know this? Because we can measure it. When you have current flowing through a wire, two things happen. First, an electric field appears around the wire. This comes from the voltage, the potential difference that's pushing the electrons. Second, a magnetic field appears around the wire. This comes from the moving charges, the current itself. These aren't theoretical. You can measure them with instruments. They exist in the space around the wire. And when you have both an electric field and a magnetic field in the same region of space, at right angles to each other, something remarkable happens. Energy flows in a direction perpendicular to both fields. This is called the Poynting vector. discovered by a physicist named John Henry Poynting in 1884, and it tells you exactly where energy is flowing. Not through the copper, through the space. Now you might be thinking, okay, that's a neat theory, but does it actually matter? Does it change anything? Oh, it matters. It changes everything about how we understand energy. If this is already breaking your brain, hit that like button, because we're going deeper. In the mid-1800s, a Scottish physicist named James Clerk Maxwell did something extraordinary. He unified electricity and magnetism into a single theory. Before Maxwell, people thought electricity and magnetism were separate phenomena. Sure, they were related. Everyone knew that currents create magnetic fields, and changing magnetic fields create currents, but they seemed like different things. Maxwell showed they weren't. Maxwell wrote down 4 equations, now called Maxwell's equations, that completely describe how electric and magnetic fields behave. And buried in those equations was something profound. Electric and magnetic fields aren't separate. They're 2 aspects of one thing, the electromagnetic field. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They're linked, inseparably, and together, they can propagate through empty space as waves. Now, what does this have to do with your house wiring? Everything. When you have current flowing through a wire, you automatically have both fields. The voltage between the wire and ground creates an electric field pointing away from the wire. The current flowing through the wire creates a magnetic field wrapping around the wire in circles. These 2 fields exist in the space around the wire, not inside the copper, around it. Now here's what Poynting figured out in 1884. When you have an electric field and a magnetic field in the same region of space, perpendicular to each other, there's a flow of energy. The direction of that flow is given by what we call the Poynting vector. The formula is simple. The Poynting vector equals the electric field cross the magnetic field, divided by a constant. What does cross mean? It means you take the direction perpendicular to both fields. If the electric field points one way, and the magnetic field points another way, the Poynting vector points in the third direction, perpendicular to both. Let's apply this to a wire carrying current. The electric field points radially outward from the wire, like spokes on a wheel. The magnetic field wraps around the wire in circles, so the electric field is radial. The magnetic field is circular. What direction is perpendicular to both? Along the wire. The Poynting vector points along the length of the wire, but outside the wire, in the space around it. That's where the energy is flowing. Not through the copper, through the electromagnetic field in the space around the copper. You might think, okay, so energy flows outside the wire instead of inside. So what? The wire still carries the energy, right? Wrong. The wire doesn't carry anything. The wire guides the field. Think of it like a road. The road doesn't carry cars. Cars move on their own. The road just tells them where to go. The wire doesn't carry energy. Energy flows through space. The wire just shapes the electromagnetic field so that energy flows in a useful direction. And this has massive practical consequences. Because if energy flows through space, not copper, then you don't actually need copper to transmit energy. You just need the right electromagnetic field. Let me give you a thought experiment that makes this really clear. Imagine you have 2 parallel wires, separated by, say, 1 centimeter of air. One wire carries current out, the other carries current back. Between them is just air, empty space, maybe some plastic insulation. Now, where is the energy? Between the 2 wires, there's an electric field. Why? Because one wire is at a higher voltage than the other. The voltage difference creates a field in the space between them. There's also a magnetic field. Why? Because both wires have current flowing through them. Those currents create magnetic fields that loop around each wire. So in the space between the wires, in the air, you have both an electric field and a magnetic field, which means you have a Poynting vector, which means energy is flowing through the air. The energy isn't in the copper. It's in the electromagnetic field in the space between the wires. The copper is just there to create the field, to shape it, to guide it. But the energy itself? It's flowing through empty space. This isn't speculation. This is measurable reality. Let's look at a real-world example. A coaxial cable. You know these. They bring internet to your house. Or, they used to, before fiber optics. A coaxial cable has a center conductor, a copper wire, an outer shield, also copper, and insulation between them. Now, where does the energy flow? If you believe the old water in a pipe model, you'd say it flows through the center conductor, but it doesn't. The energy flows through the insulation. through the supposedly non-conductive material between the center wire and the outer shield. Why? Because that's where the electromagnetic field is. The center conductor and the outer shield are at different voltages. That voltage difference creates an electric field in the insulation. The center conductor carries current. That current creates a magnetic field wrapping around it, also in the insulation. Electric field in the insulation. Magnetic field in the insulation. Therefore, Poynting vector in the insulation. The energy flows through the plastic, not the copper. Engineers who design high-frequency circuits have to account for this. At low frequencies, like 60 Hz household power, most of the energy is in the conductors. But at high frequencies, radio waves, microwaves, light, almost all the energy is in the fields, not the conductors. In a fiber optic cable, there's no conductor at all, just glass. Pure electromagnetic waves. In a radio antenna, energy radiates into space. No wires needed. It's all electromagnetic fields. And this leads to something even more profound. If electricity is just electromagnetic fields propagating through space, then what's the difference between electricity and light? If you're still with me, leave a comment telling me which part shocked you the most, because we're about to unify everything. What is light? Most people would say, light is photons, or light is electromagnetic waves, and they'd be right. But here's what they miss. Electricity is also electromagnetic waves. Light and electricity are the same phenomenon, just at different frequencies. Let's think about what's actually happening in each case. Electricity in a wire. An electromagnetic wave propagating along a conductor. Frequency, very low. Maybe 60 Hz, maybe a few megahertz for radio signals, guided by copper. Light, an electromagnetic wave propagating through space. Frequency, very high. Hundreds of terahertz, not guided. Free propagation. But physically? Same thing. Oscillating electric and magnetic fields, perpendicular to each other, carrying energy through space. The entire electromagnetic spectrum is one continuous phenomenon. At the low end, radio waves, microwaves, the electricity in your walls. At the high end, infrared, visible light, ultraviolet, X-rays, gamma rays, different frequencies, different names, but the same underlying physics. All of it is electromagnetic energy propagating through space via oscillating fields. This means that when you flip a light switch, what you're really doing is launching an electromagnetic wave down a guided path. It's not fundamentally different from shining a flashlight. You're just using copper to guide the wave, instead of letting it spread out freely. The energy in both cases travels through space, through electromagnetic fields, not through matter. Your Wi-Fi router? Electromagnetic waves at 2.4 or 5 gigahertz? Your microwave oven? Electromagnetic waves at 2.45 gigahertz? Your phone talking to a cell tower? Electromagnetic waves at various frequencies depending on the technology. Your light bulb? Electromagnetic waves at hundreds of terahertz. All the same physics. All energy flowing through space via electromagnetic fields. This fundamentally changes how we think about matter and energy. Matter, copper wires, your body, the earth, is mostly empty space held together by electromagnetic fields. And when energy moves, it moves through fields, not through matter. Matter is just a way of organizing fields. Energy is a property of fields. Everything is fields. Now, if energy flows through electromagnetic fields in space, what's the wire actually for? If energy flows through space, why do we even need wires? Why not just transmit energy wirelessly everywhere? Great question. And the answer reveals something important about engineering versus physics. Physically, you don't need wires. Energy can flow through empty space with no guidance at all. That's what radio is. That's what Wi-Fi is. That's what light is. But here's the problem. If you let electromagnetic energy spread out freely, it goes everywhere. You send out a signal from a transmitter. It spreads in all directions. Most of it misses the receiver. It's incredibly inefficient. Wires solve this problem. A wire doesn't carry energy, but it guides the electromagnetic field, so energy flows in a specific direction. Think of it like a garden hose. The hose doesn't create water. The hose doesn't power the water. The hose just makes sure the water goes where you want it. Wires do the same thing for electromagnetic energy. They shape the electric and magnetic fields so that the Poynting vector, the energy flow, points in a useful direction. With wires, you can transmit energy with very little loss. Modern power lines lose only about 6% of energy between the power plant and your house. If you tried to do that wirelessly, just beaming energy through the air with no guidance, you'd lose more than 99% of it. So we use wires, not because energy travels through them, but because they're efficient guides for electromagnetic fields. But in cases where wires aren't practical, we do transmit energy wirelessly. Radio and TV broadcasts, cell phone signals, Wi-Fi, Bluetooth, wireless charging for your phone. All of these work on the same principle. Electromagnetic fields carrying energy through space. No wires needed. The trade-off is efficiency. Wireless power transmission wastes a lot of energy. But for communication, where you're sending information, not bulk energy, it's worth it. Nikola Tesla understood all of this back in the 1890 seconds. He built enormous towers designed to transmit electrical power wirelessly across vast distances. He demonstrated that it worked. You could light bulbs with no wires, just by putting them in the right electromagnetic field. But it was incredibly inefficient. Most of the energy radiated out into space uselessly. So we went with wires instead. Not because Tesla's physics was wrong, it was right. But because the engineering economics didn't work out. So now you know. Energy flows through space via electromagnetic fields. But there's one more thing I need to tell you. And it's going to tie everything together. Something is flowing through the wires. The electrons. And the electron flow is important. It creates the magnetic field. Without moving electrons, you don't get a magnetic field. Without a magnetic field, you don't get a Poynting vector. Without a Poynting vector, no energy flows. So the electrons aren't carrying the energy, but they're necessary for energy to flow. They're like the engine of a train. The engine doesn't carry the cargo. But without the engine, the cargo doesn't move. Here's the full picture. When you connect a circuit, an electric field propagates along the wire at nearly the speed of light. This field comes from the voltage source, the battery or power plant. That electric field pushes on electrons in the wire, making them drift slowly through the copper. Those drifting electrons create a magnetic field that wraps around the wire. The electric field and the magnetic field, together, create a Poynting vector in the space around the wire. Energy flows along that Poynting vector, through space, guided by the wire. When the energy reaches a load, a light bulb, a motor, a heater, the electromagnetic field does work on the electrons in that device. Those electrons convert electromagnetic energy into light, motion, heat, or whatever else the device is supposed to do. When I first learned this, I felt cheated. All those years I'd been told that electricity flows through wires like water through pipes. And it's not true. It was never true. But here's what I came to realize. The truth is so much more beautiful. Electricity isn't mechanical. It's not little particles bumping along a tube. It's fields. Invisible patterns of force that fill all of space. Patterns that can carry energy, transmit information, and make the modern world possible. Maxwell figured this out in the 1860 seconds. Poynting figured out the energy flow in 1884. And we've been using these principles to build technology ever since. Every time you flip a light switch, you're manipulating electromagnetic fields that extend through space. You're conducting an invisible orchestra of electric and magnetic force. And that is so much cooler than water in a pipe. So the next time someone tells you that electricity flows through wires, you can tell them the truth. Electricity doesn't flow through wires. It flows through space. And the energy that powers your entire life is traveling through invisible fields all around you. Right now, all the time. If this changed how you see electricity forever, make sure you subscribe. Because next week, we're diving into quantum field theory. If everything is fields, what are particles? The answer will blow your mind. And leave a comment. Did you know energy flows through space, not wires? I read every single one. Thanks for watching. And remember, the next time you turn on a light, you're not pushing electrons through copper. You're shaping invisible fields in empty space. That's physics. That's reality. That's beautiful. See you in the next one.